So I wanted to take a moment to recap a lot of the stuff I talked about in the last couple of videos. So I talked about forces, and before that, I talked about kinematics. Let's connect all of these and figure out how they relate to each other. So, how does work relate to forces? What equation relates the two?
Fs cosine phi.
Yeah, if the force is constant, you can just do Fs cosine phi. Just to keep it general, let's say that the force is varying. So you would do an integral. So integral from x1 to x2 of f in the x direction dx. That's in general what you do. So that's what relates work and force.
So we could have done it that way for the last example, but it was just a simpler way.
That's true. This is the general case where the force is varying, and this is basically what the integral simplifies to if the force is constant. So you could have used this if the force is constant too. I mean, you can quickly see how it's the same thing. You can take fx outside the integral, and you get fx times x2 minus x1. And x2 minus x1, that's just displacement, which I call s. And f in the x direction is just f cosine phi. So it basically turns into this. All right, so that's what relates work and force. So what connects forces and kinematics?
F equals ma.
Exactly. Because of the acceleration in F equals ma, you can do a lot of stuff with acceleration and relate it to speed and all that stuff. So the equation that connects forces and kinematics is that the net force equals ma. Okay, so now the next question is what relates work and kinematics? That's what we're going to figure out right now. The question we're really answering is how is the total work done on a particle of mass m by a net force related to its speed? So we're trying to relate total work done to speed. So let's start with a general equation. Let's assume that the force is variable, that it varies. The total work done is the integral from x1 to x2 of some net force in the x direction. We'll call that f sub x dx. We're trying to relate this to speed, trying to relate this to kinematic stuff. So let's write f as ma. Let's get acceleration in there. So we know f in the x direction is just m times a in the x direction. Again, we're trying to connect this to speed. How does acceleration relate to v, basically?
Good. Derivative of velocity with respect to time is acceleration.
Absolutely. So we know a sub x is just d v sub x dt. So this is good, but the thing is this integral is with respect to x, and this is dt right here. So I want to make this a dx kind of situation. So I can just use the chain rule. I can say that this equals dv dx times dx dt. What is dx dt?
Oh, well, that's just v.
Absolutely. So this is just vx, v sub x, and we have times this derivative right here, dv dx. All right. So what I can do right now is I'm going to be very physicsy and multiply both sides by dx. And we have ax dx right here, right? So I can just replace it with vx dvx. The only thing is that now my integral is with respect to vx, so I have to make the bounds with respect to vx now. So instead of x1 to x2, this is going to be v1 to v2.
This is very calculusy.
Yes, so now we have a relationship between work and speed. So let's just do this integral. It's a pretty simple integral. So what's the integral of mvx with respect to vx?
M is a constant, so just leave that outside.
Mhm.
You raise by one power and you divide by that power.
Yeah, so the integral is just going to be 1 half mvx squared. And I'm going to plug in v1 and v2. So when you do that, you get that the total work done on a particle by some net force is 1 half mv2 squared minus 1 half mv1 squared.
Well, that just looks like a difference of kinetic energies.
Yes, very good point. The quantity 1 half mv squared is called the kinetic energy of the particle. So I can just write this as K2 minus K1. And K2 minus K1, I can just say that's delta K. So this is called the work energy theorem. Basically, the work done by the net force on a particle equals the change in the particle's kinetic energy. Now that we know this, think about work this way. If you accelerate an object to a greater speed by applying a force to the object, you're going to increase the kinetic energy of that object, right? Because v is increasing. And if you decelerate the object to a lesser speed by applying a force, you decrease the kinetic energy of the object, right? Because v went down. You can say that your force has transferred energy to the object from yourself, or you can say from the object to yourself. So think of work as energy transferred to or from an object via a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. So work is basically transferred energy, and doing work is the act of transferring the energy. That's why work has the same units as energy, and it's a scalar quantity. Okay, so back to this diagram here. So what relates work and kinematics is the work energy theorem. So basically, this equation right here. Let's do an example. I had fun with this example too. So
Those are the scary ones.
you are bringing a birthday gift to a friend who is upstairs in his house. To reach him, you must slide the gift up a ramp that makes an angle theta with the horizontal, leading from the ground floor to his room. Your friend is a vertical distance h above the bottom of the ramp. The coefficient of kinetic friction, oh, I didn't write of, I wrote
Yeah,
coefficient.
you got to read it as is. Like
Oh,
you don't want to change the problem. So
oh, unfortunate.
the coefficient kinetic friction between the gift and the ramp is mu k. Continue.
Okay. Determine the minimum speed you must give the gift at the bottom of the ramp so that it just reaches your friend at the top. Let's draw a picture of what's happening.
But the gift is going to be a physics textbook, and your friend will be very disappointed.
Very,
Your friend was expecting a Krispy Kreme donut, but instead, my friend's getting your physics problem.
yes, a different kind of treat. Okay, so this is the ramp and it makes an angle theta with the horizontal. And here is the gift. I'll just draw a box. What else do we know? We know that your friend is a vertical distance h above the bottom of the ramp. So I'm going to just label this as h. Okay. So that's pretty much all we know. We also know mu k. So what forces are acting on the gift?
We can have gravity and the normal force again.
Yes, we have mg downward. We have normal force perpendicular to the ramp. And we have a coefficient of kinetic friction, so there's going to be some kinetic friction. The question is, in which direction is the kinetic friction?
Well, it's got to oppose the direction of motion.
Yes. So since we are sliding the gift up the ramp, kinetic friction is going to be down the ramp like this. Let's define our coordinate system. Just like last time, along the ramp is going to be the parallel direction, and perpendicular to the ramp is the perpendicular direction. Also, let me put a subscript k here. We're trying to find the minimum speed you must give the gift at the bottom of the ramp. speed, we just saw speed right here. So we're gonna have to use the work energy theorem.
Energy theorem.
Yes. So it says that we're trying to figure out the minimum speed so that it just reaches your friend at the top. So that means that when the gift reaches the top of the ramp, the speed will be 0. So that means this V2 will be 0. So this term is going to cancel out. So let's figure out what the total work is, and then we can find the minimum speed V1. We have to ask ourselves, are the forces constant? And the forces are constant here. So we can use Fs cosine phi. Since this is the total work done, that means the F in the Fs cosine phi is going to be net force. So let me write that in. We're going to look at the net force in the parallel direction because that's where the acceleration is. So basically, work total is going to be the sum of the forces in the parallel direction times s times cosine phi. And this is going to equal negative 1 half mv1 squared. And
That's not a dot product on the left, right? Because these are scalars.
oh, yeah, that's just times. I could just leave it like this. The only thing is that the net force is in what direction? Let's figure out what that is. Is it going to be up the ramp or down the ramp? I mean, just looking at these forces, everything in the parallel direction is down the ramp. And then everything else in the perpendicular direction is going to cancel out. So we have,
I, yeah, I just thought of it as like it's slowing down as it goes higher up the ramp intuitively.
that's
So the acceleration must be down the ramp.
that's also a good way of thinking about it. Acceleration is going to be down the ramp, so the net force will also be down the ramp. The velocity vector gets shorter and shorter basically as you go up the ramp. But yeah, the net force is down the ramp. And the displacement S is up the ramp because that's where it's moving. When we're using this equation, Fs cosine phi, we're using magnitudes here. So I know this is going to be negative. So let me put an absolute value on this because we're just dealing with magnitudes. Let's figure out what this equals. We don't know s. We know phi. These vectors are just 180 degrees apart. So we know phi. We just don't know s, and we don't know the net force in the parallel direction. So let's figure out what that is. The net force in the parallel direction, I can just break this up into its parallel and perpendicular components. So this is mg perpendicular. This is mg parallel. The net force in the parallel direction is going to be negative mg parallel because it's in the negative parallel direction. And also f sub k is in the negative parallel direction. So I'm going to also subtract f sub k. This angle will be theta, and we can use random guy's trick and we can say that sine makes it slide. So mg parallel, it's opposite theta, so it's mg sine theta.
It's not my trick, it's the internet's trick.
And what do we know about kinetic friction? Is there a formula for that?
It's just the normal force times the coefficient.
Yeah, of
So
kinetic.
n mu k.
Yeah, so let me just write that formula down. So recall F sub k is mu k, which is given in the problem, times n. So I can substitute that here. So let's see. We don't know m, we know g, we know theta that's given in the problem, we know mu k. So we don't have n. So let's find n. So n is in the perpendicular direction. So let's look at the sum of the forces in the perpendicular direction. So what's the acceleration in the perpendicular direction?
Gotta be zero, it's not moving up or down in that direction at all.
Yes. And what are the sum of the forces in the perpendicular direction?
Normal minus mg in the
Just say perpendicular.
direction.
Yes. The sum of the forces in the perpendicular direction is just n minus mg perpendicular. And yeah, a perpendicular is 0. So you can add mg perpendicular to both sides, and it's adjacent to theta, so it's mg.
So which keeps it close.
Yeah,
That's how you.
yes, yes, cos keeps it close, so mg cosine theta. So I'm gonna replace that here. Instead of n, I'm gonna put mg cosine theta now. We have everything here except mass. Before I do anything with the m, let me factor out negative mg. Let's do that just to make it a little cleaner.
We like clean.
Yeah, so negative mg, and you're going to be left with sine theta plus mu k cosine theta. Okay, so now I can plug this in here, and you'll see the m's will cancel. And we're using the magnitude of the net force. So this negative here is going to go away. So you're going to have mg times s cosine phi equals negative 1 half mv1 squared. And like I said, the m's will cancel. So there's one thing left that's stopping us from finding v1, and that's s. We don't know s. How does h, the thing we're given, relate to s?
We know theta.
Yeah,
We know trig.
absolutely. So h is opposite that angle, so we know sine of theta is h over s, because remember the hypotenuse is s. And you can multiply both sides by s, divide by sine theta, and you'll get s equals h over sine theta.
And you could write that as h cosecant theta if that's what is your biscuit.
Yeah, I'm gonna keep everything sine, cosine, and tangent because of the calculator. So
So you know it's a physics class, not a math class.
absolutely. So let me plug that in here. And remember, phi is 180 degrees because the net force vector and the displacement vector are anti-parallel. So I'll just plug that in.
I love it when the negatives cancel out. So satisfying.
Yes, very exciting. Cosine of 180 degrees is just -1, and that's just going to cancel out with this negative here. And what I can do is I'm going to distribute this 1 over sine because I can cancel it out with this sine here. So I'm going to do g times h. And when I distribute the 1 over sine, you get sine over sine here. So that's 1 plus mu k cosine theta over sine theta, which is cotangent theta. But I'm going to write that as 1 over tangent theta. And this equals 1 half v1 squared. So v1 is the minimum speed. All I have to
And by 2 square root.
exactly. So V1 equals 2GH times 1 plus mu k over tangent theta and square root of all that.
Looks so much prettier when there's no numbers.
I agree. So that's the minimum speed. So you have to use the work energy theorem here. And since we're doing work total, we're using the magnitude of the net force. And we have everything, right? We know G, we know H, we know mu K, we know theta. So everything is in terms of the stuff that was given in the problem. All right. So just remember to keep that in mind.